Our final speaker for this session is Zane Crawford from Michigan State University. His field is in electromagnetics, and his advisor is, I'm going to try to pronounce this, Shankar Balasubramaniam. Okay, if I butchered that, I'm sorry. But he did his practicum at Sandia National Laboratories at Albuquerque, New Mexico in 2017.
All right. Thank you, everyone, for staying for my talk. This is work that I did also with collaboration with a fellow student, Scott O'Connor, and my advisors, Dr. Lucas Lind and Dr. Schenker. And this is a project that I'll be handing off predominantly to Scott afterward. But the flow of this talk is we're going to motivate why we're looking at particle and cell methods, then just a brief review of the particle cell method itself and how we came about wanting to implement it in a finite element framework. We're going to go over 2 formulations for that finite element framework and then show some results and summarize. So what are we trying to do? Particle and cell methods are a way to represent how plasmas move as a representation of particles. And it has practical applications as far as doing Z machines, particle accelerators. We just have a quick example of having some object, this cathode oscillator and a magnetron, that you have some flow of electrons that you want to model and to see what kind of oscillations you get out, what radiation happens. And over the past decades, many codes have come about, such as IcePick, Magic, Empire, that are able to simulate these things, but they're mostly based on the finite difference time domain method. And we're going to show that there's been a lot of advancements in simulating electromagnetic phenomena, and we want to see if we can use those advancements in numerical methods to pair with this existing particle and cell method. So what are we trying to do? We're trying to represent our sources, which is our charge density rho and our current density J, and we're going to represent them with some distribution function F. And that distribution function has to obey the Vasilov equation, and to make it the Maxwell-Vasilov equation, we're just going to represent our acceleration using the Lorentz force there. And that force is applied by electric fields and magnetic flux density that has to obey Maxwell's equations, namely the 2 Krell equations, Gauss's law, and our boundary conditions, which enforces the fact that the tangential component of our electric field needs to be continuous, and the normal component of our magnetic flux density has to be continuous. And that's going to be relevant later on. And so once we know that we're moving around these particles and have these electric fields that apply the forces to move these particles around, we can come up with this cycle where we are going to move our particles and then have the sources deposited onto our grid, our rho and our j, and use those to solve for our electric fields that we're going to use to push the particles again, and do that cycle over and over again. And hopefully, in that process, we're going to have charge conservation. We won't have a buildup of charge, and we also have current continuity, which we'll discuss later. Now, the underlying way that we solved for these electric fields and magnetic flux densities, magnetic fields for previous particle and cell formulations, is that we use the finite difference time domain method, in which you have these staggered grids where you represent your fields on the edges and your fluxes on the faces. And the nice thing about finite difference time domain is that they have all your relationships as far as the derivatives and the orthogonality of the fluxes and the fields, and no spurious charges arise from using this method. It's great, and we just have a figure here that you have a staggering of these 2 grids that you stagger in time, and you are able to evolve your fields, push your particles. The problem is that when it comes down to representing more advanced geometry, things that have curves, this becomes more difficult with the finite difference time domain method. You're trying to represent something that's smooth with a bunch of squares or cubes. And there are some methods that have arisen that will try to cut some of the cells to alleviate that problem, but there's other issues as well. The fact that your time step size is severely limited by your CFL condition, that your wave can only propagate so far every time step with respect to your cell sizes, and that higher order descriptions in time and space are difficult to implement. And so there was a big push to say, well, what other methods have we developed? What other ways can we solve for these fields that may improve that? And it's tempting to look at finite element method. Except in my field, when they were first looking at it, they tried to do it with the wave equation, the vector wave equation, which has some problems with it. The fact that in the vector wave equation, you have this null space that has a time-growing gradient function. And if you can imagine, if that permissible solution gets introduced to your electric fields, as you evolve in time, you're building up charge, because that time-growing portion of it in Gauss's law, you're going to accumulate charge. And furthermore, that nice thing about the finite difference time domain method, where your fields are nice and continuous, if you introduce new material properties, a dielectric, let's say in your domain, you need those discontinuities we talked about earlier. Your electric field, the normal component, needs to be discontinuous. That's not possible in finite difference time domain method, and that was a challenge that they struggled with the finite element method when they co-opted it from mechanical engineering. They actually had to come up with a new basis set to allow for that discontinuity in the normal component. And there was a lot of work to it. There's been some recent successes with it, but at the same time, there was work done that said, instead of trying to solve the vector wave equation, let's discretize Maxwell's equations directly and to use different basis functions to represent your electric field and your magnetic flux density, such that you have the right basis sets to represent your charges and your currents as you deposit them. And that method was developed by several different ones across different fields, Balsa-Vida and Kettinen in the electrical engineering community, Peter Monk from math, and even Daniel White from Lawrence Livermore now worked on this method. But it was only in the past 5 or 6 years that applications to the particle and cell method was really done, and pretty much in 2D. So what are we doing? Well, we have two different basis functions, the Whitney edge and face basis functions, that live on the edges and the faces of your grid. And the nice thing about these basis functions is that the way that you build them together follows the flow of how you expect your potentials and fields to be related to each other. Take a gradient potential, you get a field. A curl of a field, you get a flux. Take a divergence of a flux, you get a charge. And the nice thing about it is that these basis functions have the boundary conditions that we expect. The fact that for our fields, they're only going to have tangential continuity along the edges, and then the face elements only have normal continuity across the faces. And with that, we can use that to represent our electric field, our magnetic flux density, do some variational approach, and we're able to get the system of equations. We take finite differences in time, stagger them so we can get an energy conserving system, and we have a nice time marching scheme, which for the lowest order is kind of cool, that the way that you discretize Faraday's law, it's an explicit update, but for Ampere's law, it's an implicit update. You do have to invert that mass matrix. But to represent our charges, we have to give them some sort of shape function. That way we can discretize it and map it to the grid. So just to make our math kind of easy, we're going to say that our distribution function f can be represented as delta functions. And so we can discretely represent our charges and our current density in this manner here. And in a continuous sense, we need to have charge conservation. That time derivative of our charge density needs to be equal to the negative derivative of our current density. That if you have charge leaving a place, it needs to be equal to the amount of current flowing away from it. The trick is because we're living in a discrete world, we need to make sure that we use the right measurement function to make sure that we have charge conservation and current continuity. So we need to, when we're measuring our current density and mapping it to our grid, and to make sure that we have our satisfied charge continuity, we need to measure it with some basis set that is essentially normal to the faces of our function. And furthermore, when we apply our discrete divergence operator, we want it to collect in the EB scheme that we're talking about right now, we want it to collect at the nodes. And that's exactly what that operator does, where all the edges connected to a single node will have that current contribution there. Okay. And beautifully, the basis functions that we use for the EB scheme, that's exactly what happens, that the basis functions connected to that node connect there. Trick is that the magnetic field doesn't necessarily, it's not obvious how you make sure that it satisfies Gauss's law. So instead, we can come up with a dual formulation where we use the same basis sets for our fields, except now our field is the magnetic field, our flux is the electric flux density. We just rewrite our Maxwell's equations in terms of D and H, and then we're able to come up with a very similar time marching scheme, except now our Ampere's law is explicit, Faraday's law is implicit. And our discrete divergence operator now, instead of collecting at nodes, it collects inside the tets. And the nice thing about that now is now we're able to come up with ways to filter our currents such that we have better noise properties. And furthermore, just move on because we're running out of time. The basis sets that we use are the correct normal basis sets naturally when we move to this dual scheme in D and H. So just to simple preliminary results, just to prove that things work, if we have a particle experience a magnetic field and give it some velocity, we see that we don't have any drift, and these are all 3D results. And if we allow it to march on in time very quickly, we see that the errors are pretty controllable, and it's mostly dominated by our Boris push. If we use our dual scheme, whether we use our surface normals directly or the face element basis set that we had, we note that we incur no additional error as we extend it for long periods of time. And even if we run it for, say, a number of time steps, we don't see an increase in error. Furthermore, to make sure that we have nice charge conservation and current continuity, we have a plasma ball where we have an overlap of electrons and protons such that the initial fields are 0, but we just let that relax. The ions are very heavy. And we note that as we let it evolve in time, we don't see any hot spots, that we aren't collecting charge in weird ways. A very similar test that we have is that we have a particle beam where we have an anode and a cathode. We apply a voltage across it and then let particles enter into the simulation. And we note that we don't have any striation of our particles as it evolves in time, that we have a nice smooth expansion as it crosses the tube that we have. Furthermore, we can compare this against existing 2D codes and note that there's pretty good agreement in the expansion that we have. If we take a 2D slice of our 3D simulation and lay it across their 2D simulation, we note that we're seeing very good agreement between existing validated codes. And furthermore, as we stated, that the basis set that we're using and the way that we're measuring it, we have pretty good control of our current continuity. Experimentally, you have to have very, very good current continuity in order to not see any striation of the particles as you advance it in time. So in summary, we have come up with different ways to use the basis set used for the mixed finite element method to make sure that we're properly measuring our sources, our charge density and our current density, such that we can come up with two different formulations for the finite element method to do particle and cell simulations. And we're building a 3D benchmark suite so that we have a nice class of problems and use it for practical applications. And in the future work, we're going to create periodic systems, develop more interesting test cases, and then also do some of that filtering I talked about to improve the noise characteristics of the simulation. Thank you.